All right, let's jump right in. We're going back in time, back to the 1970s, to talk about a chip that didn't just power computers, it powered a whole hidden technological revolution. This is the story of the Intel 8085, the true unsung workhorse of the microprocessor world.
You know, to really get why the 8085 was so special, you have to picture the world it was born into. In the mid-70s, if you wanted to build a computer system, you were wrangling a whole mess of different chips. The CPU was just one piece of this really complicated, power-hungry puzzle. It was a problem just begging for a simpler, more elegant solution.
I mean, just look at its predecessor, the famous Intel 8080. It was a great chip, for sure, but man, was it needy. To get that thing up and running, you needed not one, not two, but three separate power supplies. We're talking plus 5 volts, minus 5 volts, and plus 12 volts. That's just more parts, more complexity, and a bigger headache for anyone trying to design with it.
And then, in 1977, Intel drops the 8085, and it was a total game changer. It took everything that was great about the 8080, but it integrated the clock and the system controller right onto the same piece of silicon. And the best part, it ran on just a single, standard plus 5 volt supply. That little 5 in its name? Yeah, that's exactly what it's for, and believe me, it made all the difference.
So, what was this new, simplified chip actually capable of? Come on, let's pop the hood and take a quick look at its core specs.
Okay, so at its heart, the 8085 was an 8-bit processor, which was pretty standard for the time, and it chugged along at a respectable 3 MHz. But its real genius was that simplification. By packing in key components and being 100% software compatible with the older 8080, it just made life so much easier for engineers. But the real key to its power, that was its 16-bit address bus, and that's where things get really interesting.
You see, a 16-bit address bus means the processor can access 2 to the power of 16 unique memory locations. You do the math, and that comes out to 65,536 bytes, or what we know as 64 kilobytes. Now, 64 KB might sound tiny to us today, but for a piece of industrial equipment or a simple computer in the late 70s, that was a massive amount of space to work with.
So we know what it is, but how does it actually think? To get that, we need to peek inside at its own internal memory, its super-fast scratchpad called the register array.
Yeah, this quote nails it, but let me put it this way. Think of that 64 KB of main memory as a giant library. The registers, they're the desk you're working at. You don't run back and forth to the shelves for every single little calculation, right? No, you bring the books you need to your desk where you can access them instantly. That's exactly what registers do for a CPU.
Let's look at the big ones. First, you've got the accumulator. That's the star of the show. It's where all the addition, subtraction, and logic actually happens. Then you have the program counter. Think of it like a bookmark that's always pointing to the very next instruction the chip needs to run. And the stack pointer, that thing is crucial for managing a temporary workspace in memory called the stack, which helps it keep track of different tasks.
Now, here's a really clever trick. You had these general-purpose registers, B, C, D, and E, that were each 8 bits. But the H and L registers could be paired up to work together as a single 16-bit register called HL. So why do that? Well, a 16-bit number is exactly what you need to point to any address in that 64 KB of memory. This little feature made the 8085 incredibly efficient at fetching and moving data around.
Okay, so we know about the storage, but how does the 8085 actually deal with a running system? You know, executing commands and, maybe more importantly, responding to things happening in the outside world.
Well, the key to all of this is something called an interrupt. And an interrupt is, well, it's basically a doorbell for the processor. Imagine the CPU is busy, deep in thought running a program, and all of a sudden, the keyboard needs to send a character. It rings the doorbell. It sends an interrupt signal to get the processor's attention right now.
And the process is just so elegant. The doorbell rings, the processor finishes the very last instruction it was working on, puts a bookmark in its place, and goes to answer the door. It runs a special little mini program to handle whatever's needed, that's the interrupt service routine, and then it goes right back to its main task, exactly where it left off. This is really the foundation of modern multitasking.
But here's the thing, not all doorbells are created equal. The 8085 has this built-in priority system. NTR is kind of your standard doorbell for everyday things. The RST interrupts are for more important visitors. But trap? Trap is the fire alarm. It's a non-maskable interrupt, which means the processor absolutely cannot ignore it. It's saved for true emergencies, like a power failure. giving the system one last chance to save critical data before the lights go out. So how do you manage all these potential interruptions? Well, the processor has a special instruction called RIM, which stands for Read Interrupt Mask. It lets the program quickly check which doorbells are enabled and which ones have been temporarily silenced or masked. It's kind of like the processor's own internal caller ID and do not disturb system all rolled into one.
The 8085 was, without a doubt, a brilliant piece of engineering, but it didn't exist in a vacuum. Its legacy was really shaped by its main competitor and the very different markets that each ended up dominating. And that competitor was the legendary Zilog Z80. The Z80 had a richer set of instructions and, crucially, a built-in circuit for refreshing memory chips, which made it cheaper to build those early home computers that needed a lot of RAM. And that's why you see the Z80 in all those iconic machines, like the TRS-80 and the Sinclair ZX Spectrum. The 8085, with its focus on high integration and simple power needs, found its real calling somewhere else entirely.
And that is the real story of the 8085. It became the undisputed king of the embedded world. It was that hidden brain inside industrial controllers, lab equipment, and just countless other devices that needed to be smart, but without the cost and complexity of a full-blown computer. It truly was the ultimate unsung workhorse.
So the 8085 is this perfect example that the most important technology isn't always the flashiest one grabbing the headlines. It's often that quiet, super reliable component working tirelessly behind the scenes, which kind of makes you wonder, doesn't it? What are the unsung workhorses of our modern world? What are the tiny, powerful brains hiding in plain sight all around us today?
Have you ever really stopped to think about how a computer chip, just this tiny little piece of silicon, can actually, well, think? I mean, it takes in numbers and instructions, and somehow it spits out a logical result. It feels like magic, doesn't it? But it's not. It's actually a beautifully choreographed dance of logic and electricity.
So let's pull back the curtain on this whole thing. To really get a grip on it, we're going to look at a classic piece of tech. Because if you can understand how this 40-year-old chip does some simple math, you'll understand the fundamental principles that power literally every single computer we use today.
And our guide for this journey is the Intel 8085. This thing was released way back in 1977. It's an 8-bit microprocessor, which means it was a complete central processing unit, a CPU, all on one chip. Now, it was an update to the famous 8080, but the 8085's real trick was that it needed less extra hardware to work. That made it a total workhorse for all kinds of things, from early computers to all sorts of industrial gadgets. And the way it works, it's the perfect blueprint for understanding how computation really happens. Okay, so where inside this little chip does the actual thinking happen? Well, it happens in a specific neighborhood of components we can call the ALU group. That stands for Arithmetic and Logic Unit. This right here is the computational core of the whole microprocessor.
First up, you've got the most important 8-bit register in the whole system, the accumulator. You can just call it Register A. The best way to think of it is as the main workbench. If you're going to do a calculation, one of your numbers almost always starts here. And, just as important, when the job is done, the final answer gets stored right back here on the workbench.
But wait a minute, math usually takes two numbers, right? So where does the second one hang out? It's held in something called the temporary register. This thing is the accumulator's essential, behind-the-scenes assistant. It's totally internal to the CPU, so as a programmer, you never even see it or mess with it directly, but it plays a vital role, holding that second number just for a moment, right before the calculation kicks off. And that brings us to the star of the show, the Arithmetic Logic Unit, the ALU. This is the calculator. This is the brain of the operation. It grabs its two inputs, one from the accumulator workbench and one from that secret helper, the temporary register, and it does the actual work. It doesn't matter if it's adding, subtracting, or doing some logical comparison like an and or an or. This is where it happens.
So how do all these parts actually work together? Well, let's trace the journey of one single instruction, let's say adding two numbers. It's a really simple, kind of elegant 5-step process that basically reveals the very core of what computing is. The key thing to understand is this flow of data. So imagine the CPU gets an instruction like add B. That just means add whatever value is in register B to the value in the accumulator.
So first, the value from register B gets whisked over to the temporary register. Then, the ALU instantly grabs that value and the one already in the accumulator and, boom, adds them. The result immediately overwrites whatever was on the workbench. But we're not quite done. There's one final, absolutely critical step that has to happen. And that final step involves another really special register. See, after the ALU does its job, it doesn't just give you an answer. It also tells a story about the answer. And that story gets recorded in what's called the flag register. You can think of it like a scorecard for every single calculation the CPU makes. Now, what you're looking at here is a map of that scorecard. The flag register is really just a collection of 5 individual bits, and we call them flags. Each one of these flags answers a very specific yes or no question about the result of the operation that just happened. And this right here is how a CPU makes decisions. And this table breaks down exactly what those questions are. Was the result 0? The 0 flag gets flipped to on. Was the final number negative? The sign flag gets set. Did the addition create a number that was just too big to fit in 8 bits, causing it to overflow? That's what the carry flag is for. These little flags are what let a program ask things like, hey, jump to this other part of the code, but only if the last result was 0. This is the absolute foundation of all logic in every piece of software ever written. Now, the 8085 was a really capable chip, for sure, but it didn't exist in a vacuum. To really get its place in history, you have to know about its legendary rival, a chip that would go on to totally dominate the home computer market. So on one side, you've got our 8085. It had this really elegant design that needed fewer support chips, which made it the perfect choice for what we call embedded applications, things like traffic lights or scientific instruments. But then you had its rival, the Zilog Z80. The Z80 had more instructions and some cool built-in features like a memory refresher. This made it cheaper and way easier for designers to build the home computers of the late 70s and 80s. We're talking the TRS-80, the Sinclair ZX Spectrum. The Z80 basically became one of the most popular 8-bit CPUs of all time because of it. But here's the most important takeaway from all of this. That simple sequential dance that we just watched, data moving from a register to the ALU, the result getting stored, and the flags getting set, that is the fundamental building block of computation. Every single app on your phone, every website you visit, every video game you play, at its absolute core, it's just a mind-bogglingly huge number of these simple operations, all happening at unbelievable speeds. Which kind of leaves you with a final thought, doesn't it? When you strip away the billions of transistors, the multiple cores, all the layers of software, is the most powerful supercomputer on Earth really just a much, much faster and more ridiculously complex version of that same simple, elegant idea that was humming away inside that little 8085 chip back in 1977? It's something to think about. Hey everyone, and welcome. Today, we are going to peel back the cover on one of the most important chips in computing history, the Intel 8085. We're going to look right past all the pins and the plastic packaging to see where the real thinking happens, right there on the processor's own internal workbench. All right, let's jump in. So, let's kick things off with a pretty big question. I mean, we all know that computers compute, but how do they actually hold on to the information they're working with in any given microsecond? Where does it keep the numbers and instructions it needs right now? Well, that's the puzzle we're going to solve today. And the answer to that puzzle is a little thing called a register. Now, the absolute best way to picture a register is to think of a chef's countertop. It's not the big pantry way in the back. That's kind of like your main system memory, your RAM. No, the countertop is that small, super fast, instantly accessible workspace, where the chef, our CPU, keeps the exact ingredients it needs for the step of the recipe it's working on this very second. Okay, first up, let's meet the most fundamental tools in the 8085's entire toolkit. These are the registers that are doing almost all of the heavy lifting, the day-to-day handling of data. Meet the team. These are the 6 general-purpose registers, and they have really simple names: B, C, D, E, H, and L. Each one of them can hold an 8-bit piece of data. You can just think of them as the CPU's personal high-speed scratchpad, where it quickly jots down numbers while it's in the middle of a calculation. Now here's where things get really clever. These registers have this awesome dual nature. They can totally work on their own as individual 8-bit registers for small jobs, but, and this is the cool part, they can also team up into 16-bit pairs, BC, DE, and HL. This lets the 8085 work with bigger numbers, or even more importantly, 16-bit memory addresses, all without needing totally separate, bigger registers. It's just incredibly efficient design.
All right, so we've seen the registers that actually hold the data. Now, let's take a look at the two special registers that are basically in charge of directing the entire show. They're the brains behind the operation.
First up, we have the program counter, or just PC. The 16-bit register is the absolute heart and soul of program execution. Its one and only job is to hold the memory address of the very next instruction the CPU needs to go and grab. And after every instruction, this specialized bit of hardware called the incrementer/decrementer latch automatically points it to the next one. This is so important because it means the main part of the CPU doesn't have to waste cycles on a simple counting task. It's what keeps the whole program chugging along.
And next to it is the stack pointer, or SP. So if the program counter is the foreman reading the blueprint, the stack pointer is like the person stacking plates at a cafeteria. It manages a special area in memory called the stack, which works on a last-in, first-out basis. You know, the last plate you put on the stack is the first one you take off. When the program needs to pause to handle a quick task, it pushes where it was onto this stack, and the SP's job is to always know where the top of that pile is.
So here's a quick look at how that actually works. Let's say we do a push operation. The processor doesn't just write the data. First, the stack pointer's value is decremented by 2. It actually moves down to make room. Then, the 16-bit value gets stored at that new, lower memory address. This little dance ensures the stack grows downwards in memory and, crucially, that nothing gets accidentally overwritten.
Okay, let's pull the curtain back even further, because beyond the registers that a programmer can see and control, the 8085 has a couple of secret helpers working behind the scenes that are absolutely essential to how it gets things done. I'd like you to meet the W and Z registers. These are temporary 8-bit registers that the CPU uses as its own private little scratchpad. So when it's running a more complicated instruction, say swapping the contents of 2 other registers, it can use W and Z to shuffle the data around without messing up the values that you, the programmer, have carefully put into B, C, or D. They are completely invisible to your code. You can't access them, you can't control them, and that is exactly what makes them so useful. So we've met the whole team, right? We've got the general-purpose workhorses, the navigators that control the flow, and even the secret helpers behind the scenes. So let's see them all work together in the most fundamental rhythm of the CPU, fetching a single instruction from memory. This right here is the heartbeat of the processor. In the very first clock cycle T1, the program counter puts the address of the next instruction out onto the address bus. In T2, the CPU sends out a read signal, and memory responds by putting that instruction's code onto the data bus. By T3, that code gets loaded into the CPU's own instruction register, and then in T4, it finally gets decoded and executed. This 4-step dance happens over and over and over for every single instruction. And that, right there, brilliantly sums up the definition of an instruction cycle. It's that whole process, the fetch, the decode, and the execute. That is the fundamental unit of work for any microprocessor, then and now. So just think about it. The 8085 managed to do everything with basically a dozen registers you could actually talk to. It's just a masterpiece of elegant, efficient design. And that brings me to a final thought. The modern processor in the phone or computer you're using to watch this works on the exact same principles, but it doesn't have dozens of registers. It has thousands, tens of thousands. It's a truly staggering scale, but it's all built on the simple, powerful foundation we've just explored. Thanks so much for joining me. Okay, let's dive right in. Have you ever really stopped to think about how a computer chip thinks? I mean, not in some abstract way, but what's actually happening inside that little black square when you give it a command? Well, today, we're going to take a journey deep inside one of the true legends of computing to see exactly that. Our guide for this trip is the one and only Intel 8085 microprocessor. Now, this chip might not be famous like the ones in your phone today, but it was the hidden hero, the secret brain in tons of devices for decades. So how did this one little chip get so popular? Well, the secret is all in its incredibly smart and simple design. And this quote right here, it just hits the nail on the head. This was the 8085's superpower. See, it wasn't about being the absolute fastest or most powerful chip out there. It was about being practical. It cut down on the number of extra parts you needed, which meant it was cheaper and easier to build a computer around it. And that opened the floodgates for engineers to put a digital brain into almost anything you can imagine.
So let's properly introduce our hero. The 8085 wasn't just another piece of silicon. It was basically a revolution crammed into a tiny 40-pin package.
What we're looking at is a complete 8-bit central processing unit. It was the follow-up to the already famous Intel 8080, but it had this one key advantage, a real game-changing feature that made it an absolute star, especially in the world of embedded systems. And this was it. Just one single positive 5-volt power supply. That's all it needed. Now, to put that in perspective, its older brother, the 8080, needed 3 different power sources, plus 5 volts, minus 5 volts, and plus 12 volts. Can you imagine the headache? This one change made designing a circuit board so much simpler and cheaper. It was a massive deal. Okay, so we've got this powerful, practical little brain, but how do we talk to it? How do you tell it what you want it to do? Well, like any brain, it's got its own language. And to get anything done, we have to learn the vocabulary. So at the very top, we have what's called an instruction. It's just a basic command to get the processor to do something specific. You can think of them as verbs, really. Add this, move that, jump over there. Simple, direct actions. But here's the thing, the 8085 doesn't read words like add, it speaks in ones and zeros. The real command, the raw binary pattern that the silicon actually understands, is called an opcode, which is short for operation code. This is the chip's native language. So how do programmers write code without losing their minds typing out long strings of ones and zeros? That's where mnemonics come to the rescue. They're just short, easy-to-remember codes for us humans, like MOV for move. Then, a program called an assembler does the boring work of translating our friendly mnemonics into the binary opcodes the CPU actually needs. And this right here, this is its entire vocabulary. Every single command the 8085 can possibly execute is on this list. Each one of those mnemonics, like AMDB, has its own unique 8-bit opcode. In this case, it's the binary pattern for the number 80. That's the language right there. All right, now that we know the language, let's actually follow an instruction on its incredible journey. It all starts when the CPU needs its next set of marching orders. It has to go out to memory and retrieve or fetch the next command. This is called the opcode fetch cycle. And this all happens in a super precise 3-step dance, all timed to the chip's internal clock. These steps are called T-states. So in step 1, T1, the CPU puts an address on the address bus. It's basically shouting out to the memory, hey, I need the info at this specific spot. Then in T2, it sends out a read signal, which says, okay, I'm ready for it now. And finally in T3, the memory puts that instruction, that opcode, onto the data bus, and the CPU grabs it and brings it inside. This timing diagram shows you that dance in stunning detail. It might look complicated, but it's just a visualization of that electrical ballet happening. You can see how all the different signal lines have to go high or low at the perfect instant, all within a few millionths of a second. It's just incredible. Okay, the opcode has been fetched. It's made it inside the CPU. But it's still just a pattern of ones and zeros. What does it actually mean? Now we get to the heart of the matter, the real thinking part. The instruction has to be decoded. So the very first stop for our newly arrived opcode is special little holding area called the instruction register, or IR. You can think of it like a temporary inbox. The opcode just sits there for a moment so the CPU can take a good look at it before any action happens. And from that inbox, the opcode gets handed off to the real star of the show, the instruction decoder. This is the central command center. Its whole job is to be the CPU's master translator. It looks at that binary pattern in the instruction register and figures out exactly what needs to happen next. This is where a simple string of bits gets turned into a concrete action plan for the rest of the chip. And here's the really clever part. The decoder communicates what it found by setting these special status lines. You see them here, IO/M, S1, and S0. Based on the instruction it just decoded, it sets up these lines to tell the entire system what the very next machine cycle is going to be. So if it just decoded a load data instruction, it sets these lines to memory read for the next cycle. It's always thinking one step ahead. But what happens if something urgent comes up while our instruction is on its journey? What if some external device needs the CPU's attention, like right now? Well, this is where things can take an unexpected turn, all thanks to something called interrupts. The 8085 has a few of these special input pins that act like emergency hotlines straight to the CPU's core.
And they have a strict pecking order. So if a couple of things happen at once, the CPU always knows what's most important. Trap is the big one. It's the highest priority, and it always gets answered first, no matter what. Now, you might be wondering how a programmer keeps track of all this. Well, the 8085 has this incredibly useful instruction called RIM, which stands for Read Interrupt Mask. When you run it, the CPU grabs an 8-bit status report. And each individual bit in that report, which you see laid out here, answers a specific question. Hey, is an interrupt waiting? Are interrupts even enabled right now? Are there any I'm supposed to be ignoring? It's a brilliantly simple way to get a full system status in a blink of an eye. So, when you put it all together, that whole journey of a single instruction, from being fetched from memory to being decoded in the heart of the chip to finally being executed, and then you repeat that millions of times every second, well, that's how you get the incredible lasting legacy of the 8085. So why are we still talking about this chip today? Because that combination of being simple to use, having everything integrated, and having just enough power was the perfect recipe for the embedded world. That reliable, predictable instruction cycle we just walked through made it the perfect, invisible brain for everything from traffic lights and medical devices to the first generation of industrial robots. And that really leaves us with something to think about, doesn't it? The 8085 was this amazing, simple brain for the machines of its era. Today, we're surrounded by tiny microcontrollers that are almost unbelievably more powerful. So the question is, what kinds of revolutions will these new, simple brains power for us tomorrow?
All right, today we're cracking open a true classic of silicon, the Intel 8085 microprocessor, to tackle a really big question.
So, how does this little slice of engineered sand take a command, something as simple as add these two numbers, and actually do it? I'll tell you, it's not magic, but it is an incredible piece of choreography.
You know, the best way to think about it is like a tiny nervous system. It's constantly firing off these perfectly timed electrical pulses to all the different parts of its body, telling them exactly what to do and, crucially, when to do it. Everything has to be in perfect sync.
Okay, so let's dive right in. If this chip is a whole orchestra, who's the conductor? Who's waving the baton and making sure every single section plays its part right on cue? Well, meet the star of our show, this brilliant little component called the timing and control unit. This thing is basically the brain of the brain. It doesn't do the math itself, but it's the one generating all the signals that tell everyone else when to fetch, when to calculate, and when to save a result. It's the ultimate micromanager.
And it has got a lot to manage. I mean, it's got to coordinate the arithmetic logic unit. That's the calculator part. It's directing traffic between all the registers, which are like tiny little scratch pads for data. It's telling the memory when to send the next instruction, and it's handling all the chatter with the outside world. It is a very, very busy job.
Now, to make all of this happen without creating total electronic chaos, everything has to follow a super strict rhythm, a constant, unwavering beat that drives every single action inside that chip.
And this is where it gets really interesting, how time is broken down. The biggest piece of time is an instruction cycle. That's the whole process, start to finish for one command. But that's made up of smaller machine cycles, which are basic steps like, say, fetching something from memory. And each of those is built from the tiniest unit of all, the T-state. That's one single tick of the chip's internal clock.
So, get this. Even the most basic action isn't instant. Just grabbing a single command, what's called an opcode, from memory takes anywhere from 4 to 6 of these clock ticks. In that impossibly small fraction of a second, this whole perfectly coordinated dance of signals has to happen.
So, how does our conductor actually talk to the orchestra? Well, it uses a very special language, a language made of electrical signals.
One of the most important words in this language is ALE, which stands for Address Latch Enable. See, the 8085 was all about efficiency, so it used the same physical wires, the bus, for both addresses and data. ALE is the signal that basically shouts, "Hey everyone, what's on the bus right this second is an address. Grab it now." Because a moment later, that same bus is going to have data on it, and thanks to ALE, everybody knows the difference.
Then you've got the two most fundamental commands, read and write. When the read pin goes low, the control unit is telling a memory chip, "Hey you, put your data onto the bus for me." When the write pin goes low, it's saying, "Okay, get ready, I'm about to put data on the bus for you to save." It's literally the difference between asking for information and giving it.
And this table here, this is just brilliant. This is how the rest of the computer knows what the processor is up to. The control unit sets these 3 status lines at the start of every single machine cycle. Just by looking at the combination of ones and zeros, any other chip knows instantly if the processor is about to do a memory read, a memory write, or as you see right there, an opcode fetch. It's like a public status update for the whole system.
Okay, so we've got the rhythm, we've got the language. Let's put it all together. Let's watch the 8085 perform its most common and most important task.
We're going to follow, step by step, tick by tick, the entire process of an opcode fetch. This is the moment a line of your code starts its journey to becoming a real action.
All right, watch this. T-state 1. The CPU puts an address on the bus and pulses ALE. That's the "here's where we're going" signal. T-state 2. Now that the address is locked in, the processor pulls the read line low, basically saying, "Okay, memory, give me what you got." T-state 3. The instruction byte flows from memory right into the chip's own internal register, and the read signal turns off. And finally, T-state 4. The control unit decodes that instruction, and if it's a simple one, it just executes it right down in there. Boom! All of that in just 4 ticks of a clock.
Okay, that was a pretty deep dive, I know. So let's zoom back out. Why go through all this trouble? Why is this microscopic, high-speed ballet so incredibly important?
Well, the absolute genius of the 8085 was its elegant simplicity. Its design stuck things like the clock generator right onto the chip, which meant you needed fewer parts to build a whole computer. Using that multiplex bus we talked about, that made systems way cheaper to build. And this fundamental dance, fetch, decode, execute, it's the direct ancestor of the billions, literally billions of operations your phone or computer is doing right this second.
And don't just take my word for it. This quote comes straight from the original datasheet. By making the address lines and the data lines share the same physical pins, Intel massively simplified things for everyone. This was a huge step in making computers more accessible to all of us. Now, this whole time, we've been assuming the processor is just humming along doing its own thing. But what happens if you press a key or a new piece of data comes in? That's where interrupts come in. They're basically external signals that shout, "Hey, conductor, stop what you're doing, I need you now." It's the nervous system's reflex action, and yeah, it's another critical job for our timing and control unit.
And that really brings us to the final kind of mind-blowing thought. This precise 4-step dance we just walked through, it was perfected on a chip from 1977. The very device you're watching this on right now is performing a vastly faster, way more complex version of that exact same process, billions of times over, just to put these images on your screen. It all comes back to a conductor, a rhythm, and a perfectly timed set of signals.
Today, we're talking about a chip that's more than just old tech. It's a masterclass in clever engineering. We're looking at the Intel 8085. This thing was a huge step away from those super complex, multi-chip computers and a major leap towards the all-in-one systems we have today.
You know, to really get why the 8085 was so cool, you gotta look at the problem it was designed to solve. Back in the 70s, its older brother, the Intel 8080, was a real powerhouse, but it was also incredibly needy. It required a whole squad of other chips around it just to function. Building a computer back then was like putting together a puzzle with way too many pieces. So here's the game plan for this explainer. We're going to start with how the 8085 cleaned things up. Then we'll dive into its really clever bus multiplexing trick. We'll take a peek inside at the registers, see how it handles interruptions, put it all together, and then wrap up with its long-lasting impact. All right, first up, let's talk about the 8085's main job, simplifying the whole computer building process that the 8080 made so complicated. Yeah, the 8080 was a total game changer, no doubt. But it couldn't work alone. Think of it like a brilliant artist who needs 3 assistants just to mix the paint. Any system you built around it was just inherently more complex and more expensive. And this slide really lays it all out. It shows the pure genius of the 8085. The 8080 on the left, it needed 3 different power supplies, plus 2 separate support chips just for basic timing and system control. Now look at the 8085. It only needed a single, standard, plus 5-volt supply, and it basically swallowed the jobs of those 2 support chips right onto its own silicon. This was huge. It massively reduced the number of parts you needed and made designing a computer so much simpler, practically overnight. Okay, now for the real magic. Let's get into the clever little trick that made all this integration possible on just a standard 40-pin chip. So picture yourself as an Intel engineer back then. Here's the puzzle you have to solve. A CPU needs to talk to memory.
It uses an address bus to say where to find stuff, and a data bus to actually move that stuff back and forth. For the 85, that meant you needed 16 pins for the address and another 8 for the data. That's 24 pins already. Add in power, ground, and all the other control signals, and you just run out of space on a 40-pin chip. So what do? The solution was just beautiful. You make the pins do double duty. It's a technique called bus multiplexing. It's kind of like instead of having separate roads for cars and trucks, you have one road, and you just change the traffic signs to say cars only for the first minute and trucks only for the next. So first, let's look at the simple part. The 8085 has a set of 8 pins that are part of what's called the address buffer. Their only job is to carry the upper half of the memory address. That's it. This is a one-way street. The CPU sends the address information out, and that's all these pins ever do. And here is the really clever bit. The other 8 pins, the ones labeled AD0 through AD7, make up the data/address buffer. At the very beginning of any operation, they act as the address bus, carrying the lower half of the address. But then, just a moment later, they completely switch roles and become the 8-bit data bus, a two-way street for data to flow either into or out of the CPU. Just brilliant. Right, but you might be wondering, how does the memory chip know when those pins are carrying an address versus when they're carrying data? Well, that's the job of this absolutely critical signal, the address latch enable, or ALE. Think of it like a traffic cop. The 8085 sends out a quick pulse on this ALE pin that basically yells, "Hey memory, the address is on the bus right now. Grab it quick." And this slide shows that whole dance perfectly. Look at the T1 state. The CPU puts the full address out there and ALE goes high. Then, as ALE drops, some other chip out there grabs and saves that low address. By T2, the 80 bus is totally free, so the CPU sends out the read signal. And finally in T3, the memory puts the data that was requested back onto that very same bus so the CPU can grab it. It's this perfectly timed, super efficient sequence. Okay, so we've seen how the 8085 talks to the outside world. Now let's pop the hood and take a quick look at its internal workspace. So, these registers are basically the CPU's high-speed scratch pad. You've got the accumulator, the A register, which is the main workbench for all the math and logic. B, C, D, and E are just for general temporary storage. H and L are special, though. You can pair them up to create a 16-bit pointer to a specific spot in memory. And then you have the stack pointer and the program counter, which are essential for managing the program's flow and always knowing what to do next. Now, a processor can't just be off in its own little world running code. It needs a way for external things, like a keyboard or a hard drive or a timer, to interrupt it and say, "Hey, I need your attention right now." And that signal is called an interrupt. It's really just like a tap on the shoulder. When the CPU gets an interrupt, it stops what it's doing, saves its place, and then jumps to a special little program, an interrupt service routine, to handle whatever that request was. So what happens if a bunch of things try to interrupt at the same time? Well, the 8085 has a priority system built right in. Trap is the big one. It's what we call non-maskable, which means the CPU absolutely cannot ignore it. It's for critical stuff like a power failure warning. All the others, from RST 7.5 down to INTR, are maskable, which just means the programmer can write code to tell the CPU to ignore them if they're not important at that moment. And how does a programmer actually control all of this? They use an instruction called RIM, which stands for Read Interrupt Mask. When you run this command, it loads a status byte into the main register. And as you can see, each bit is like a little flag. Bits 0, 1, and 2 tell you which interrupts are currently being ignored, while bits 4, 5, and 6 tell you if any interrupts are waiting in line. It's basically a quick way for the software to check up on the hardware status. Okay, so we've looked at the hardware tricks, we've seen the internal logic. Now let's just zoom out a bit and see how all these pieces fit together to get things done. Pretty much everything the 8085 does boils down to one of these 7 basic operations, or machine cycles. It doesn't matter if it's grabbing the next instruction, reading from memory, or writing to some external device, it's executing one of these fundamental actions. And that elegant bus multiplexing dance we talked about earlier, that happens inside every single one of these memory and I/O cycles, all timed perfectly by the chip's internal clock. So, after all this clever design and engineering, what was the 8085's real impact? Where did this chip actually end up in the world? And this quote really hits the nail on the head. While a more complex chip, the Z80, won a lot of the early battles for the home computer market, the 8085's pure simplicity and elegance made it a superstar in a completely different field, embedded systems. Because you could build a working computer with pretty much just an 8085 and a memory chip, it became the go-to brain for countless things, like industrial controllers, printers, and all sorts of other dedicated gadgets for years and years. And that really leaves us with something to think about. The 8085 was this perfect example of doing more with less. It solved a really complex problem not by adding more stuff, but by being incredibly clever with what it already had. And it's a great reminder that sometimes the most powerful solution is actually the most elegant one.
You know, when you think about these old microprocessors, it's kind of mind-boggling, right? How did a simple chip from the 70s even begin to deal with the messy, unpredictable real world? How could one tiny piece of silicon possibly juggle multiple things at once? Well, today, we're going to look at a classic chip that had a very, very clever answer. So let's really break this down. The core problem, it's all about attention, isn't it? How can a single brain, or in our case, a single little processor, stay focused on one thing, but also be ready for, well, anything else that life throws at it?
All right, picture this. You've got a chef totally in the zone, working on some super complex recipe. But then, ding, goes the oven. The doorbell rings, and their phone starts buzzing all at once. What do? Which one do they deal with first? This is the exact problem we're talking about.
And that right there, that's the dilemma at the heart of any early microprocessor.
You see, a CPU is a lot like that chef. At its core, it's just plugging away, executing one instruction at a time in a nice, orderly line. But the outside world, keyboards, disk drives, all that stuff, they don't care about its schedule. So how does the CPU deal with these urgent, unexpected events? It can't just keep stopping and asking, hey, you need anything? How about now? That would be crazy inefficient.
And this is where our hero, the Intel 8085, steps onto the scene. A chip from 1977 that came up with a really, really elegant solution.
Okay, so the Intel 8085 was a total game changer. For one, it only needed a single 5-volt power supply, which was a huge deal back then compared to its predecessor. And it packed the clock and system controller right onto the chip itself. This made building computers way simpler and cheaper. But the real magic, the absolute genius of the 8085, was how it handled those interruptions.
So how did they do it? What was the secret sauce? Well, it all comes down to a super powerful idea called the interrupt system.
So what's an interrupt? Think of it like a tap on the shoulder for the CPU. Instead of the processor constantly having to check in on every single device, the devices themselves get to say, hey, over here, I need you. It's a signal they send when they're ready for something, like when you press a key on a keyboard. In this process, it's like a perfectly choreographed 4-step dance. First, the signal comes in. The processor doesn't just drop what it's doing. It carefully puts a bookmark in its current task, saving its exact spot. Then, it jumps over to run a special little program called an interrupt service response. That's the code that handles whatever the request was. Once that's all done, it goes right back to its bookmark and picks up like nothing ever happened. It's our chef quickly running to the door and then coming right back to the cutting board.
Okay, but wait, what happens if the oven dings and the doorbell rings at the exact same time? Yeah, the 885 had a brilliant answer for that too.
So the chip itself has these 5 dedicated hardware pins just for these interrupt signals. You've got trap, RST, 7.5, 6.5, 5.5, and INTR. This means you could have up to 5 different external things, all vying for the CPU's attention at once.
But here's the really cool part, and what this table shows so well. These interrupts are not all created equal. Nope. They are hardwired into a fixed priority system. The 8085 always knows that a TRAP signal is the most important thing, followed by RST 7.5, and so on, all the way down to INTR. It's like having a built-in triage nurse.
And this is maybe the most important distinction of all. That top priority interrupt, trap, is what we call non-maskable. Think of this as the fire alarm. The CPU cannot, under any circumstances, ignore it. It's reserved for absolute emergencies, like a power failure where the system gets one last gasp to save critical data. All the others, they're maskable. That means a programmer can actually write code to tell the CPU, hey, for the next few moments, just ignore those. I'm doing something really important. It's like putting your phone on Do Not Disturb.
All right, so that covers the urgent stuff. But besides handling emergencies, the 8085 also needed a really simple way to just, have a conversation with the outside world.
And for that, it had two special pins, SID for serial input data and SOD for serial output data. This was a super straightforward way to send and receive information just one single bit at a time. It was perfect for talking to simple devices like a keyboard or a basic terminal without needing all the complexity of the big 8-bit data bus.
And this slide, this is where the pure design elegance just shines through. The 8085 has this one instruction called RIM, which stands for Read Interrupt Mask. Now look at this diagram. With one single command, a programmer could check on two totally critical systems at the same time. It reads the current status of all the pending interrupts, which ones are waiting, which are disabled, and at the very same time, it grabs the value on that serial input data line. I mean, that's just an incredibly efficient way to combine interrupt control and serial I/O into one beautiful instruction.
So what's the big takeaway here? Why are we still talking about a chip that's almost 50 years old? What's the legacy?
Well, as this quote says, the 8085 became an absolute workhorse. It was everywhere, especially in embedded systems. The hidden little computers inside traffic lights or lab equipment. Its flexibility and the fact that you didn't need a ton of extra chips to support it made it a go-to for designers.
But the bigger picture, the really crucial point, is that this whole interrupt-driven way of doing things was a foundational leap forward. It's what allowed a single, pretty simple processor to manage a complex, unpredictable world. It literally paved the way for the responsive, interactive machines we all take for granted today. I mean, this is the direct ancestor of the system that lets you listen to music on your phone while it's also downloading your email and tracking your GPS location.
And that leaves us with one final kind of mind-bending thought. The Intel 8085, it was a master juggler for its time, but its world was limited to just those 5 interrupt lines, which back then was revolutionary. But now, think about your phone. It's built on the exact same fundamental principles, but to handle every tap, every swipe, every notification, and all those background apps, it's managing not 5, but tens of thousands of these interrupts, every single second. It just goes to show you how a brilliant idea from the 1970s didn't just survive, it scaled up to become the very bedrock of our entire digital world.
All right, let's dive in. We're going to talk about something really fundamental for any microprocessor. How in the world does it find its data? I mean, think about it. Telling a chip to add something is kind of useless if it doesn't know what to add or where to find it. So today we're going to look at how a true classic, the Intel 8085, solves this exact problem.
So how does a chip like the 8085 figure out where to look? Is the data just packed right inside the instruction? Is it sitting in some super fast internal storage? Or is it somewhere out in the main memory? Well, the answer is pretty much all of the above. The different ways it does this are called addressing modes, and they're absolutely key to making the whole thing work efficiently. And that's where we get to the core idea for today, the addressing mode. The best way to think about it is like a GPS for the processor. It's the specific method an instruction uses to find its data, or as we call it, the operand. Every single instruction that moves or changes data has one of these addressing modes built right into its DNA. And here's the cool part. The 8085 doesn't just have one way of doing things. It's got this whole toolkit of 5 different addressing modes, and each one is perfectly suited for a specific kind of task. So let's break them down one by one, starting with the simplest. Okay, first up we have immediate addressing. And you know what? The name kind of gives it away. The data is available, well, immediately. With this mode, the data the processor needs is literally a part of the instruction itself. It doesn't have to go on a scavenger hunt to find it anywhere else. The instruction basically says, hey, do this operation, and by the way, here's the exact value you need to do it with. A perfect example of this is the instruction MVI-A05H. This tells the 8085 to move immediately the hexadecimal value 05 straight into its main workspace, a special register called the accumulator or register A. See? The data, that 05H, is right there in the command. No mystery. So how does this actually work? Well, it's super direct. When the processor grabs the MVI instruction from memory, that 05H value comes right along for the ride. The chip's control unit sees the command and the data all at once and just shuffles that value straight to its destination. It's simple, clean, and perfect for loading constant numbers into the processor.
Now, immediate addressing is great for constants, but what if the data you need is already inside the chip? That's where our second mode comes into play, register addressing. This one is all about speed, about moving stuff around inside the chip itself. In this mode, the instruction tells the processor that the data it needs is already sitting in one of its own high-speed storage lockers, which we call registers. Think of these like the processor's personal workbench. We're not going out to the main memory toolbox. We're just shifting something from one internal pocket to another. Take a look at an instruction like MOV A, B. It's as straightforward as it sounds. Move the stuff from register B into register A. The instruction doesn't contain the actual data. It just points to the source and destination, these little storage spots right there on the chip. And the big win here? It's all about speed. Because this whole data transfer happens on the processor's internal highway, its internal data bus, it is one of the fastest things the 8085 can do. There's zero delay waiting for slower external memory chips to wake up and respond. Okay, so we've got data inside the instruction itself, and we've got data already inside the chip's registers. But what happens when the data we need is way out there in the main system memory? Well, that brings us to our third mode, direct addressing. With direct addressing, the instruction itself contains the full 16-bit memory address where the data is hiding. It's like the instruction says, hey, the data you want isn't in here, but it's at this exact address. Go get it. It's a perfect map to the data's location. A fantastic example is LDA 2500H. This stands for Load Accumulator Direct. This is basically an order telling the processor, go to memory location 2500 hex, grab the 8-bit value you find there, and load it into my accumulator, now. So what happens here is the processor talks to the memory outside of it. It sees the instruction, takes that 16-bit address, and puts it out on what's called the external address bus. Then it sends out a read signal. The memory chip at that exact spot sees the signal, puts its data onto the data bus, and the processor just grabs it. Now, direct addressing is great, but you can see how it's a little rigid, right? The address is hard-coded. What if you want more flexibility? That leads us to our fourth, and you could argue one of the most clever modes, indirect addressing. So get this, the instruction itself doesn't have the address. Instead, it points to a couple of registers working together, a register pair, and says the address you're looking for, it's stored over there. It's like having a note that tells you where to find the real note with the address on it. The classic instruction for this is MOV A, M. This looks super simple, but it is incredibly powerful. Now that M is the magic part. It's not a register. It's more like a nickname for whatever memory location the HL register pair is pointing to right now. So this one instruction has to first check the HL pair to even know where to go look for the data. And that is what makes this so incredibly powerful. It's all about flexibility. A programmer can write a loop that uses the same MOVAM instruction 1,000 times. All they have to do is change the address stored in the HL pair on each pass, and that single instruction can march through a whole block of memory. This is the secret sauce for processing big chunks of data, like lists or arrays. And that brings us to our fifth and final mode, implied addressing. In this case, the instruction is so specific, so focused, that the processor doesn't even need to be told where the data is. It just knows. With implied addressing, the instruction itself is the whole story. The operation is designed by default to work on a specific hardwired register, so there's no need to point it out. The location of the data is just implied by the instruction itself. A great example is CMA. This means complement accumulator. When the 80085 sees this, it inherently knows its one and only job. Go to the accumulator, take whatever value is in there, flip all the bits, the ones become zeros and the zeros become ones, and put the result right back. The instruction is the whole story. It's totally hardwired to only work on the accumulator. Okay, let's pull it all together real quick. Immediate, the data is right there in the instruction. Register, the data is in another register on the chip. Direct, the memory address is spelled out in the instruction. Indirect, the memory address is hiding inside a register pair. And implied, the location is just fixed, baked right into the instruction. See? 5 different tools in the toolkit, each one perfect for a different kind of job. So that leaves us with a really interesting question to chew on. These 5 modes in this classic 8085 chip represent a delicate balance, a trade-off between speed, programming flexibility, and just how much memory an instruction takes up. So when you look at a modern processor with billions of transistors and way more complex needs, how do you think they juggle this exact same problem of finding data efficiently? That's a deep rabbit hole for another time. Thanks for joining me on this explainer.